Hi, I'm Matthew Levitt, and I'm presenting recent work with Ari Marcos titled Selectivity Considered Harmful, Evaluating the Causal Impact of Class Selectivity in DNNs. One common approach for understanding deep neural networks, often termed selectivity, relies on characterizing how the activity of individual neurons varies across data classes or dimensions. Notable examples include Radford et al.'s sentiment neuron, and work by Ola et al. Examining how feature selectivity contributes to classifier outputs. But evidence regarding the importance of selectivity in DNN function is mixed. Prior studies have shown selective single neurons can be essential, irrelevant, or detrimental to network performance. Furthermore, most prior studies have relied on single unit ablation, which has a number of shortcomings. We were motivated by these issues to pursue a series of experiments investigating whether selectivity is necessary and/or sufficient for DNN function, and whether it's possible to causally manipulate selectivity during training. We examined one particular form of class selectivity, defined in the equation here. As a brief intuition, a unit that has identical activations across all classes would have a class selectivity of 0, while a unit that is only active for a single class would have a selectivity of 1. Because the class selectivity index is differentiable, we can regularize for or against it directly in the loss function, allowing us to control the amount of class selectivity learned by the network's units. Our loss function consists of the standard cross-entropy loss, from which we subtract a term we refer to as the selectivity regularizer. The selectivity regularizer consists of two terms, mu-si, the mean class selectivity across all units in the network, and alpha, the regularization scale. By training networks with different values of alpha, we're able to examine the causal role of class selectivity in network performance. We used this approach for 3 models and 2 datasets, ResNet 18 trained on Tiny ImageNet, and ResNet 20 and VGG 16 trained on CIFAR 10. I only show results for ResNet 18 in this talk, but the results for ResNet 20 and VGG are similar. We started by examining the effect of decreasing class selectivity. If class selectivity is necessary for high-fidelity representations, then regularizing against class selectivity should reduce test accuracy. But if selectivity impairs network function, then reducing class selectivity should improve test accuracy. Here, I show test accuracy on the y-axis as a function of the regularization scale, alpha, on the x-axis. At the leftmost data point, alpha is equal to 0, meaning there is no class selectivity regularization. You can see that increasing the magnitude of alpha, and hence decreasing class selectivity, causes test accuracy to increase, though extreme values of alpha cause a test accuracy impairment. Here again I show test accuracy on the y-axis, but as a function of a network's mean class selectivity on the x-axis. If you start at the rightmost data point, which corresponds to alpha equals 0, which is no selectivity regularization, you can see that class selectivity can be reduced by a factor of more than 3 before it starts to negatively impact test accuracy. These results demonstrate that class selectivity in individual units is largely unnecessary for, and can sometimes even constrain, optimal performance in DNNs. But what happens if we instead regularize to increase class selectivity? Is class selectivity sufficient for network performance? Here I again plot test accuracy on the y-axis as a function of regularization scale on the x-axis, but this time for positive values of alpha, which encourages units to learn class selectivity. You can see that increasing class selectivity causes an immediate and significant decline in test accuracy, indicating that learning class selectivity beyond the levels that are learned naturally is detrimental to network performance. To directly compare the effects of regularizing to increase versus decrease class selectivity, I plot test accuracy here on the y-axis as a function of the magnitude of alpha on the x-axis. Red is the effect of increasing test accuracy, while blue is the effect of regularizing to decrease test accuracy. You can see the immediate divergence of effects with a significant decrease when promoting class selectivity and a significant increase when regularizing to decrease class selectivity. In summary, we developed a regularizer to directly promote or encourage or discourage class selectivity in individual units, and used it to show that decreasing class selectivity can improve network performance, while increasing class selectivity immediately degrades network performance. These results indicate that class selectivity in individual units is neither necessary nor sufficient for and can sometimes even constrain DNN performance. They also make a broader point about the potential pitfalls of focusing on the properties of single units when trying to understand DNNs. While we consider it essential to find tractable, intuitive approaches for understanding DNNs, it's critical to empirically verify that these approaches actually reflect functionally relevant properties of the system. Thank you very much.